In 1632, Galileo published his seminal work Dialogue Concerning the Two Chief World Systems. He was in his mid-60s by this point, and had already had multiple run-ins with the Roman Inquisition for his assertions that the Earth rotated around the Sun. So he had decided to skirt controversy and spend the intervening years quietly cementing his myriad ideas on space and the cosmos into a book. And at one point within this book, he muses on a boat. More specifically, the life of a sailor locked below deck in a windowless cabin, with plates, knives, and a goldfish in a bowl on the table, and a collection of birds, flies, and butterflies. Just what does the sailor experience? Tied up in port, the cabin is a picture of serenity. All is calm as the goldfish swims happily in his bowl. On the table, plates and cutlery remain in their place, and the flying creatures happily flutter about. But finding itself in rough seas, the cabin heaves and falls with the ship. Plates and cutlery are wrenched off the table, water spills from the goldfish bowl. On calm seas with wind-filled sails, the ship would speed up. The sailor would feel this change and see things sliding off the table. But when the wind finally drops, the ship sails smoothly on the glassy sea. Inside the cabin, all would be calm, serenity returning. For the sailor, it would be as if the ship was still in port and was not moving at all. A dropped plate would fall straight to the floor, and the sailor would sit comfortably in their chair. And it was here Galileo realized something. Without a window to reveal the truth, there are no experiments the sailor could do to reveal whether the ship was moving or not. He concluded, therefore, that there must be no absolute concept of being at rest in space. Instead, everyone must experience any smooth, uniform motion in the same way. All uniform motion must feel like simply being still. Galileo declared that any uniform motion is simply relative to any other uniform motion. And with this, the first theory of relativity had been born. Galileo's sailor floats gently on their ship on seas near the Earth's equator, rotating at 1,600 kilometers an hour around the Earth, which in turn orbits the Sun at 67,000 kilometers an hour, which in turn orbits the Milky Way at 720,000 kilometers an hour, which in turn is traveling towards the Andromeda Galaxy at 403,000 kilometers an hour. And yet, he feels nothing on this vast journey millions of kilometers from his starting point. Unfortunately, upon publishing the book, Galileo once again fell foul of the Church and was found guilty of heresy for his heliocentric view of the cosmos. The work was banned and would not be removed from the Church's Index of Forbidden Books until 1835. But this was not the end. For within a few decades of Galileo's downfall, two of Europe's greatest minds were arguing about the nature of space. One of them, Isaac Newton, was born in England in 1642 within a year of Galileo's death. He, of course, needs little introduction and is known now as one of the greatest thinkers of his age, perhaps one of the greatest of all time. And whilst not forgotten, his opponent, Gottfried Leibniz, is somewhat less well known today. Born in 1646 in what is present-day Germany, he was a leading thinker of his time, writing on mathematics and philosophy. He pondered deep metaphysical questions, including one that still haunts physicists and philosophers to this day: why there is something rather than nothing. It was in the development of calculus that the two men's feud began. Whilst Leibniz published his work first, Newton claimed that he had stolen his ideas. As president of the Royal Society at the time, Newton set up a committee to investigate the dispute. Unsurprisingly, the committee found in favour of Newton. And so, this animosity carried over to their second disagreement. A simple question: what happens to a spinning bucket of water? Space, Newton declared, was a universal absolute, a rigid stage on which motion was played out, and both space and time would exist in a universe devoid of matter to experience any motion. To argue his point, Newton asked us to think about a bucket of water. If the bucket sits at rest, the surface of the water would be flat and level. But if we spin the bucket, the water spins too and its surface becomes curved. And so Newton asked, just what is the water spinning with respect to? He claimed that the acceleration of the spin was relative to an absolute space, something separate to the object itself, and so spinning a bucket in an empty universe would also curve the surface of the water. But to Leibniz, space in an empty universe, devoid of any matter, simply made no sense. The properties of objects, Leibniz claimed, are essential in defining their meaning. Space only had meaning in the relative locations of objects, and similarly, time only had meaning when discussing their relative motions. Without matter, Leibniz said, space and time simply had no role, and hence, no existence. Sadly, Leibniz died in 1716 with the argument still in full swing, and it was Newton's ideas that stuck. Absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Absolute true and mathematical time, of itself and from its own nature, flows equally without relation to anything external. This so-called absolute space and time would be the accepted science for nearly 2 centuries, but with the caveat of Galileo's rejection of absolute rest. Relativity was still part of the argument. But that only applied to space. Time was a totally different matter. With its implicit direction, time appeared completely distinct. For Newton and Galileo, everyone's clock across the universe ticked with absolute synchronicity, a universal beat that ran through every event in the cosmos. 1 second on Earth, the same as a second anywhere else.